Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 77 in our incredible new tutorial series where you're learning how to think like an engineer using the Arduino Uno R4 Wi-Fi. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee, poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Sunfounder Elite Explorer Kit. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to teach you how to incorporate accelerometers into your Arduino projects. Well, what is an accelerometer, you ask? It is a component that measures acceleration. Now that sounds pretty simple, right? It sounds like, okay, well, it's just another sensor, but it turns out to be one of the most useful components that you can incorporate into your Arduino projects. And accelerometers are almost ubiquitous. You never think about them, but they make products that you use better and safer and faster and all types of different things like that. So accelerometers are things you don't think about, but they're already in a lot of products that you buy. So what are some examples of accelerometers? Well, there are accelerometers in your smartphone. Now you notice on your phone, when you tilt your phone in different orientations, it moves the screen. How does it know how you have your smartphone oriented? It knows that because it has accelerometers in the phone, and those accelerometers are measuring orientation, and then they are adjusting the screen based on the orientation of the phone. So that is one application. But probably the most important application, and it was actually the first application of these microelectromechanical system accelerometers that we're going to be talking about today. One of the first and most important applications was we have them in our car. Now, what are they used for in the car? They're used to detect a car crash, and if the car crashes, then the accelerometer fires the airbag. Okay. Now, you don't think about it, but that's a really, really important job, because what two things do you really want when you're driving your car? If you are driving your car and hit a wall or a pole or another car, you absolutely, positively, certainly want the airbag to fire, okay? Now, similarly, if you're driving down the highway, minding your own business, you absolutely, positively do not want the airbag to fire as you're just driving along. Because if you were driving along, if the airbag accidentally fired and hit you in the face, it's going to surprise you and you're going to crash your car and your airbag is already fired. So then you're going to really be in a lot of trouble. So that decision in an automotive application of, do I fire the airbag or do I not fire the airbag? That is a life and death decision. And you can't just fire the airbag because you hit a little bump or you maybe scrape something a little bit. You have to have the exact right conditions before you fire the airbag. Well, how do you do that? There are accelerometers in the car, and those accelerometers in many cases are the same accelerometers that I'm going to be teaching you how to use today. Pretty cool? Okay, hope it is. Hope it does sound cool. So we've talked about smartphones and tablets. We've talked about automotive systems. Also the stability control on your car, you know, where if you start losing control of your car and your car kicks in the braking systems with differential braking to try to bring your car back under control, those are these accelerometers and the same type of components that I'm going to be showing you today. There's also like these fitness trackers that you might have in a watch, or It might be a wearable device that sort of keeps track of your motion and fitness. Those have accelerometers in them. If you're using drones or robots, how do those drones stay flat and steady in their flight? Accelerometers. Okay, so while you don't think about accelerometers, they're probably some of the most useful and versatile components that there are, and so we are going to learn a little bit about them today. Now, I have to say it's something that I know a little bit about because back in the early 90s, I got some of the very first patents on these microelectromechanical system manufacturing techniques of how you can build these accelerometers on the surface of integrated circuits. And so how you build them and how you use them was something that I worked on back in the pioneering days. And like I say, I actually got some of the first patents on some of the manufacturing techniques for making these devices. So let's talk about it. First of all, what is acceleration? Acceleration is the force that you experience from either speeding up or slowing down. When you change velocity, you're either accelerating or you're decelerating. And what these accelerometers do is they measure that acceleration or deceleration. So let's jump in and see if I can kind of explain to you how these things work. Because if you were looking for a quick schematic and then copy my code and run off and do it, that's not what this channel is about. I'm going to teach you how accelerometers work, and then after you understand them, then later in today's lesson I'll show you how to hook them up and how to program them up and get them working. But first of all, let's talk about how these things work. And so I think I will come over here and let's see, give me just a second to get this thing set up. And so what we're going to do is we're going to imagine that we have this flat plate. Okay, this flat plate turns out to be very, very small. Okay, the flat plate turns out to be very, very small. But what you can do is you can imagine that this plate is like a millimeter on a side. Okay, the plate is a millimeter on a side, and I really wish that I could draw better. I just can't. This is such an important topic. I am going to go back and I'm going to draw this thing better. Okay, so let's come here like this because I've really got to kind of explain it. I really need a little bit of almost like a three-dimensional drawing. And so this is called a proof mass. Okay, and that proof mass is built on the surface of the integrated circuit. Okay, it's about a millimeter on a side and then suspended above the surface of the wafer on springs. Okay, now the springs don't really look like this, but I'm kind of drawing you a cartoon version of it here. And so there's 4 springs, and this proof mass is suspended above the surface of the wafer with these 4 springs. Okay, you could almost think of it, it's a little bit like your kitchen scales, right? You have a flat plate and you have springs under it, and then as you press down, you sort of depress that flat plate. But we're not going to be using this to measure mass. We are going to be using this to measure acceleration. Now, what I want you to think about is, think about that if you took this, right, this is sitting on the surface of the wafer. Okay, so you could think of the surface of the wafer here. It's sitting on the surface of, after the wafer is cut up, of the integrated circuit. And so the floor of the system is the actual surface of the integrated circuit. Now, what I want you to think is if you came in and you took this device and you pushed it up, like you accelerated this device up, this plate up here is going to want to stay where it is. And so as you push the integrated circuit up, what is that plate going to do? That plate is going to come down. Okay, now while it was just sitting there minding its own business, how high above the substrate was it? Well, we'll call it D naught for just the kind of default displacement while it's sitting perfectly still. But then when you press down on it, it's going to come down some, and then that distance we're going to call d. Okay, and so you went from being like this, you push it up, you accelerate up, and then that top mass comes down. Okay, well, what causes it to come down? Now we're going to go in and start kind of going through the equation. Well, it moves down because it experiences a force. The what? The force of acceleration. Now, you experience the force of acceleration if you're in the car and wham on the brakes. The force of acceleration, which in this case is deceleration, pushes you forward in your seat. If you step on the accelerator, it throws you back in the seat. So you are experiencing the force of acceleration. Well, what is that force of acceleration? Well, you probably remember that from high school physics. The force is equal to the mass times the acceleration. You are the mass, and then the car accelerates and you feel a force. This also, you think about jet fighter aircraft and they say you're pulling 3 Gs or 4 Gs or 5 Gs. What are that? What are those Gs? They are the force that the pilot is experiencing in response to the acceleration, or the force that the proof mass is feeling as you move your smartphone around. Okay, does that sound good? That does sound good. So the force that that proof mass experiences is equal to the mass of the proof mass times the acceleration that you experience. The more acceleration, the more force, and then the more displacement. Well, how much will this thing displace as a function of that acceleration? Well, you have to do that by going in and thinking about Hooke's law. Okay, so we're going to talk about Hooke's law. Again, this should take you back to your junior level physics in high school where you learned about Hooke's law. And what did Hooke's law say? Well, what force does it take to move this object that is suspended by a spring? It is going to take minus the spring constant times the displacement. So the further you want to displace it, the more force that you have to apply. Okay, and so the force goes up as you want to displace it more, or the more force you put, the more displacement you will get. Okay, and so this is the relationship between the force on the proof mass and how far it will push against those springs. And then this force is the force that mass experiences in response to acceleration. Well, what we really want to know is how far will that spring displace as a function of the acceleration. Well, I've got the force in the first equation and I've got the force in the second equation, and those two forces have to be the same. You will move in response to the force of acceleration. So those two have to be the same. So now what can I write down? Well, the force in the first one is the mass times the acceleration, and that has to be equal to, what does that have to be equal to? The Hooke's law minus k times x. Okay, what is it that is being applied? Acceleration. And then what is the result? An x displacement in that proof mass. Does that make sense? Well, what am I trying to measure? I'm trying to measure acceleration, so I want to isolate acceleration, and I can do that by dividing both sides of the equation by m, and now I'm going to have acceleration is equal to minus kx over m. How do I get m? I know m because I'm the one who made that little proof mass, so I know exactly how much it weighs. So I know m. How do I know k? Well, I made those springs, and I made those springs with a very specific spring constant. So what do I know? I know k, okay, because I made the spring. What do I know? I know m because I made the proof mass. So if I want to know acceleration, what is it that I have to know? I have to know x. Well, how do I get x? I'm going to measure x. Okay. how am I going to measure X? Well, if we look up here, back up here, again, we look up here, we have a proof mass. It is a square plate sitting over the surface of the integrated circuit, which also is a square plate. Two square plates, parallel plates, make a what? They make a capacitor, a parallel plate capacitor. And what is the capacitance of a parallel plate capacitor? It is epsilon, the dielectric of free space, which we know, we just look it up in a book. It's just a number that we know perfectly. And then the area, okay, of the capacitor divided by the D. Okay, so now what is the area? The area over here is just the area of this plate. It's the length times the width. And so we know the area. The epsilon we know. Okay, and now D is what we want to know. Well, what do we do then? We rearrange this equation where D, which is what we're looking for, is equal to epsilon A over C. We know epsilon, we know the area, and so we just measure the capacitance. It's like you put a probe on the top, you put a probe on the bottom, and you measure the capacitance. And once you know the capacitance, then you know D, the distance between the top plate and the bottom plate. Does that make sense? And now, that capacitance is just like you guys measure resistance, you measure all types of things. Well, capacitance is just a measurement, and your electronics can measure capacitance. Okay, is this making sense? I hope it does. So now, what do I know? I know that the distance is equal to epsilon A over C. Okay, and now what did I say before? That A is going to be equal to minus kx over m. Now, x is the amount that you're compressing the spring. So x is not d, x is the amount that you're compressing the spring. But what can we say that is? Well, that x is minus k over m, and then it is the distance that you're at minus the distance that you started at. Like you were here and you were here, you subtract those two, and that's the x. That's how much you have compressed. And so now I know that the acceleration is minus k, the spring constant I know, over m I know, and then d, which I can measure, right? I can measure, and the d naught I just measure before I start moving. Okay, and so now I have everything that I need in order to measure this. Okay, so what I'm going to do is for D here, since I measure capacitance, I'm going to say that the acceleration is going to be equal to minus k over m. And then what is D? D is epsilon A over the measured capacitance, okay, minus D naught. Now, do we know everything? I measured D naught to start with, and then as I am moving, as I'm going through life, I continuously measure C, okay, because as I am moving, C is going to be constantly changing. A is a constant, doesn't change. It's the area of the plate. Epsilon, the dielectric of free space, it doesn't change. M, the mass of the proof mass, that doesn't change. And K, the spring constant, that doesn't change. And so what do I have? I have an equation where I constantly measure the capacitance over here, and with that I can get a constant measure of the acceleration. Okay, does that sound good? I hope it does. Now, what is the good news? We have these devices in our Sunfounder kit. Now, earlier when we were doing the pressure sensor, we were using the GY87 module, right? We were using the GY87 module in the kit. And what did that have? That had a BMP 6050 pressure sensor on it. But what does it also have? It also has an MPU6050 IMU module. Okay, and what does this have? It has 3 accelerometers. It has one that measures acceleration in the X, acceleration in the Y, and acceleration in the Z. So it has 3 accelerometers. It'll measure acceleration this way, and this way. Okay. Now what it also has is it has a gyro that measures rotational velocity around X, a gyro that measures rotational velocity around Y, and a gyro that measures acceleration, measures rotational velocity around Z. Now what we're going to be talking about today is AX, AY, and AZ. But we also have GX, GY, and GZ. And if I were really honest with you, there is also on here, besides the BMP180 and besides the GY87 and besides the MPU6050, there is a QMC5883, which is a 3-axis magnetometer. So it will measure magnetic strength in the X, magnetic strength in the Y, and magnetic strength in the Z. And I've got a mosquito. Got him. He died hungry. You always want to make sure you didn't get bit by one of these little guys over here. So that one died hungry. We got him just in the midst of time. So I can measure acceleration in X, acceleration in Y, acceleration in Z. I can measure rotational velocity around X, but rotational velocity around Y, and rotational velocity around Z. And I can read the magnetic vector strength along X, Y, and Z. And we'll get into those things in future lessons. Now, what is the good news? The good news is this MPU6050. I hope you guys can hear that rain. There is a massive rainstorm out there. So if you're hearing a disturbance, it is the rainstorm out there. So I can measure all those things, but what is the good news? The good news is that GY87 with the MPU6050 module, it measures the capacitance and it calculates the acceleration. And what does that module report to you? It reports AX, it reports AY, and it reports AZ. So all of this stuff is done in the background. Well, if it's done in the background, why do I explain it? So you'll understand when you're using the accelerometer, you'll understand how the accelerometer works, okay? Now, man, I know I'm kind of going on a lot about this, but there's one other thing. Okay, so this, you could see, this would measure what? The acceleration in the Z direction. Now, what I would need is I would need another one of these that was turned up like this, and that's going to measure what? Acceleration in the X direction. And then I would need a third one that was turned around like that, and that would measure acceleration in the Y direction. So I would need to measure in the Z direction, in the X direction, and in the Y direction. So I would need 3 different accelerometers. Now, back in the old days, they actually did that. They had one like this, and one like this, and one like this. But then all of a sudden, some smart guys came along, and what they said is that, well, why don't we try to do it all with one? Okay. And so now, in that earlier picture, we were kind of looking from the side. But instead of looking from the side, we're going to look at these new microelectromechanical accelerometers from the top. And I'm going to show you how using one proof mass we can measure Z, X, and Y. And so let's see if I can draw this. This is a little bit tricky to draw, but I'm going to do the best I can. I'm going to do the best I can here. That was not what I wanted to do. Okay, so what we're going to do is we're going to draw the proof mass, and now you're looking at the proof mass from the top. Okay, and now what I'm going to do is I'm going to draw 2 fingers here, And while in real life there's not 2, there might be 200 fingers, I'm going to draw this as having 2 fingers on each side, and you just know in real life that it's probably 200 fingers, okay? And so I'm going to have fingers like that, and then down here I'm going to have 2 fingers and 2 fingers and 2 fingers and 2 fingers. Okay, now what I need you to realize though is that entire thing with its fingers are floating above the surface of the wafer. And so they have tiny little springs holding them up, but they're free to move this way or this way or this way. Okay, and now what we build is those are what the fingers and the proof mass are free to move. But then there are fingers that are tied to the substrate that are not free to move. And so that's what I'm going to draw. I'm going to try to draw. Okay, so here we've got this plate that is fixed to the substrate, but it comes in, it's not touching, okay, it's not touching, but it creates these other fingers like this. And then here we also are going to have some of those fingers like that. And I am just drawing these really terribly. Okay. And then here we're going to have the fingers. Maybe by the time I get to the last one, I'll draw them. But the important thing is these fingers are not touching these fingers. They're interdigitated, but they're not touching. And I kind of drew it poorly, like they were touching. Okay, so I've got fingers here, I've got fingers here, I've got fingers here, and I've got fingers here. All right, now what I want you to see is if I come in here and if I move things like this, that proof mass is going to want to stay in the same spot, and it is going to move this way if I'm pushing it that way, or it's going to move this way if I'm pushing it the other way. Well, what happens if that moves a little bit to the left or the right? This amount of overlap is going to change. This amount of overlap is going to change. And what that means is this area of overlap, the area of overlap changes, which means what? The capacitance between these fingers and these fingers change. And so if I measure that capacitance, between these fingers and these fingers, that capacitance is going to change as the proof mass moves. And similarly, if I move it this way, then what? The capacitance between this and this changes, and the capacitance between this and this changes. So I have one capacitance is going to tell me what the motion or what the acceleration in the x direction is. The other capacitance is going to tell me the acceleration in the y direction. And what? This thing is still, this whole big plate is still suspended above the substrate, and it's going to move up and down. And because it moves up and down, I can measure z acceleration. So I've just told you how to measure ax, ay, and az using this one proof mass. And that's how modern accelerometers work. They have one proof mass and they can measure acceleration in all 3 directions with that. Okay, now that's kind of how we did it in the early days. But then as we move forward, we don't want this proof mass slinging around. What if you slung it around and you ran those fingers together? They would stick. And so what we did was we realized that you can apply, what we realized is that you can apply an electrostatic force. And when your capacitor measurement is telling you that you are moving this way, you can immediately apply an electrostatic force by applying a voltage that will pull it back to its neutral position. Or if it starts coming up, you can pull it back. or if it starts coming this way, you can pull it back by applying voltages. So yes, we are measuring capacitance, but we are applying a voltage to force that proof mass not to move. And the size of the voltage that you have to apply that will force the proof mass to remain motionless, that voltage, how large that voltage is, will tell you how large the acceleration is. And so we have a forced feedback loop that holds the proof mass in perfectly still position, and from that we can then get AX, AY, and AZ. Now those very first simple things that I showed you of a plate on a spring, that's how we did it at the very start. Then how did we do it? We had a proof mass in X, Y, and Z that was moving around and measuring capacitance. We could figure out acceleration. And then the final thing that was done is we put electrostatic feedback so that we held the plate perfectly still, and we discerned acceleration by how large of a voltage you had to apply to keep the plate from moving. Okay, wow. I just condensed like 20 years of my life into 30 minutes. And so anyway, now you know how those things work. Okay, guys, put some comments down below. Am I making you weary by opening up the hood? You know, kind of like on our GPS project, what I really like to do is open up the hood and show you guys how these things work. Now, the interesting thing is, how are these made? These are made using exactly the same equipment and processes that are used to create the integrated circuits, but instead of making microscopic electronic elements, we're making microscopic mechanical elements. And around this proof mass are all the transistors and the circuitry on the same piece of silicon that apply those electrostatic forces and measure those capacitances and do the computation that then you, the user, just gets the nice acceleration out the back end. Okay, now that's enough of this nonsense of how this thing works. Let's see if we can actually get in here and turn this thing on. Let's see if we can get this thing fired up and working. So I'll need you to go to the most excellent www.toptechboy.com. I will need you to search using this happy little search icon on something like add an MPU6050 accelerometer to your project. And then you can see this is that GY87 that we were using back when we were working on the pressure sensor. You'll hook it up again. It's very simple. SDA to SDA, SCL to SCL, 5 volts to 5 volts, or that's VCC to 5 volts, and ground to ground. Okay, so that is pretty darn simple to hook up. Then you can see that I have mine hooked up here already, and it is ready to go. And so now what we're going to need to do is we're going to need to fire up your Arduino IDE. And now what we're going to do is we're going to come back over here. Hopefully I was on the right screen when I was showing you where, yeah, I think I was on the right screen when I was showing you the schematic. Okay, so we should be good now. So what we're going to do is we need to come over, and you need to come to Tools, and you need to say Manage Libraries, and we need to install the library. So I need you to search on Adafruit MPU6050. Okay, Adafruit MPU6050. I'm using version 2.2.6 if you want to use exactly what I'm doing. And then we're going to say install. And it's very important you want to install with all the dependencies. Okay, so you're installing this with all the dependencies, because some of those other dependencies are going to be used as we start turning on in future lessons the gyros and the magnetometers. Okay, I think we are ready to start coding this thing. So we're going to come up to the very top. We're in a bare minimum here, right? So let's see if we can come over here. All right, so now we're going to start needing to include the libraries. I'm going to need to include where is that? The Adafruit underscore MPU 6050 like that .h. Okay, that's good. Now I'm going to need to include And we're going to include the Adafruit underscore sensor library, which you installed as one of the dependencies. Okay, I'm trying to make sure I get this right. And then we are going to include the wire library.h. Okay, and then I like to just run this thing to make sure that I got the libraries in right. Just I like to have a little early success if possible. Make sure that we got those libraries installed. Okay, it's looking pretty happy. Try not to get my hopes up, but it does look like it's going to work. Okay. All right, and now it is downloading, and that is going to be good, so we are good to go. All right, what 3 measurements are we going to make today? We're going to be measuring AX, okay? We are going to be measuring a Y acceleration in the X direction, acceleration in the Y direction, and we're going to be measuring acceleration in the, now I'm going to let you guys do Z as a homework. Okay, so we're going to do acceleration in the X, and we're going to be doing acceleration in the Y, if that makes sense. And let me come over here. I just need to look at one thing really quick here. Give me just a second. Should have had this done before, huh? I just had a quick question I needed to get over here and make sure that I am doing the right libraries. Yeah, okay, that's very, very good. Okay, so now we're going to measure acceleration in the X direction, and we're going to measure acceleration in the Y direction. Now we're going to come down into the void setup, and I need to do a serial.begin, okay, and that is going to be at a serial.begin of 115,200. Some of the things, and don't put a comma in there, that's not, you don't put a comma in there, okay. I'm going to be running the serial monitor faster because there's going to be some times we're going to be wanting to make the measurements quickly, and so we don't want the serial monitor to be slowing us up. So we're going to be going at 115,200. Make sure over here that you select that as well when you're turning it on. We'll do that in a minute, okay? So serial.begin 115,200. Okay, now we're going to do a serial.println, and I'm just going to say MPU6050 started, like that. Okay, just let us see if we get to that line of code, and then what I'll do above that is MPU.begin. All right. Now, if I'm going to begin the MPU, I've got to define it. All right. So I've got to create that MPU object up here. And so I'm going to do the Adafruit library underscore MPU 6050 that library that we just loaded, and I'm going to create an object called MPU. Okay, and then I begin the serial monitor, and then I will begin the MPU just with MPU.begin, like that. Now there's a couple of parameters that I need to set here, and these you can set to different values, but this is a long lesson already, so I don't want to get too much into that today. We'll talk about it more later. But what I'm going to do is MPU.set accelerometer range. Okay, and so I'm going to be using MPU 6050, and then I'm going to be setting the range, and then I'm going to set it to 2G. Now that means I can measure now plus or minus 2G. Okay, now it'll go 2G, 4G, 8G. So if you're going to really be in a jet fighter aircraft or something, you might want to set it to a higher G, but I want more precision and sensitivity, so I'm setting the total range lower to the 2G setting for our application. Now similarly, MPU.set filter. Hey, that's giving it to me. Okay. I'll take it when I can get it. So set filter bandwidth, and then what I'm going to set that to is MPU6050 underscore band underscore 21 underscore hertz. Okay, now you can set this to different things, but this is just a default that will work for most things that you're going to do. So that was not the right spot there. So we're going to do MPU6050. The bandwidth is 21 hertz. All right, so that is good. Now we've got this thing set up. Now we're going to come down, and what I need to do is I need to make an event. I've got to create variables to hold the events. And so what I'm going to do is sensors underscore event underscore t. And what I want to measure is acceleration. All right. So I'm creating something that would be akin to a variable or a location or an object that I can put the measurements in, and I'm going to name it A because right now I'm measuring acceleration. Now later we're going to also measure G, and we could also measure the temperature off this thing. So you see, we could create different objects if we wanted to, okay? But I think I am just going to be today using acceleration like that. All right, now what I got to do is I've got to make a measurement, MPU.getEvent like that, and then I use this ampersand because it's kind of like a relative thing in A like that to put it in A. So I'm passing it A. It's going to put the values in A for me. Okay, does that sound good? Like that. All right, now I'm going to get the x acceleration. It's going to say A acceleration in the x direction is going to be equal to A, that object with the acceleration, and then what do I want? The dot acceleration in what? In x, like that. And then I want A y, and that's going to be equal to A dot acceleration in what? The y direction. So I make the measurement with this get event. It makes the measurement and it's sending me A. And now I'm pulling the x acceleration off of the A. But what's very important to understand is this is not making the measurement. This is making the measurement. If you just sit and keep doing this step, you're just printing or getting the same number over and over and over. If you want a fresh number, you have to do a fresh get event. Okay, so now what I'm going to do is I am going to just do a serial dot print, and what am I going to print? I'm going to print AX like that, and now I'm going to do a serial dot print, and then what am I going to print? I'm going to print a comma, okay, and then what am I going to do? I'm going to do a serial dot print, and then what am I going to print? A y like that. Okay, so I'm going to print those. I'm going to print AX and I'm going to print AY, and now I'm going to do a delay of 50 milliseconds like that. Delay of 50 milliseconds, okay? And so what we're going to have to do is this data is going to be coming through kind of quick, but it should print the acceleration in the x direction and the acceleration in the y direction. And yeah, okay, the acceleration in the x direction and the acceleration in the y direction. Okay. Let's see what happens. I probably made a lot of mistakes. I got kind of tired telling you 20 years of how accelerometers work condensed down to 30 minutes. Okay, add a fruit, no matching function called. Add a fruit. What did I do wrong? Okay. Okay, I think maybe what this wants is maybe, even though I'm not going to use them, it might want me to get all of the different numbers. And so I'm going to go ahead and say we're going to get a G and we're going to get a temp at the same time. And then I'm going to process those, and I'm going to say and G and an and temp. Okay, so I thought I could just do the ones I wanted, but maybe it wants us to go ahead and do all of them there. Let's see if that, and A and G and temp. Okay, and then AG temp. I was thinking I would just add those as I needed them, but maybe it's going to make me want to use those. I don't have to print them. We're not going to look at them because I haven't explained them yet. But to get the event, you have to make all the measurements, the accelerometers, the gyros, and the temperatures. Okay, now we need to set this thing to, 115/200. Hey, we were there already. Now, what did we do wrong? This last print should have been a print LN because it's just off to the races, off to the side of the screen. So, okay, forgot the print LN on the last one. So it'll be AX, comma, AY, new line. Let's see if we can get over here and let you see what this is. Okay. Right, there it is. Okay, so as I'm sitting there perfectly still, what is this reporting in? It's reporting in meters per second squared. Okay, it's plotting in meters per second, meters per second squared. Okay, and so as we are sitting here perfectly still, you can see that we would expect it to be reading 0 meters per second squared, and in the X direction it's measuring about 0.2 meters per second squared, and in the Y direction it is measuring 0.13 meters per second squared. So this is error, this is offset. If you look at this, it isn't moving. Okay, the other thing that I should say is if we look really closely here, you can see that the way I have this oriented, this is the X direction and this is the Y direction. So if I move it this way back and forth, where should I see the signal? In the first number. And if I move it this way, I should see the signal in the second number. So let's come back over here and let's see. And I want to move as perfectly as I can in the X direction, and the way that I do that is I'm going to lean this against this so I don't get any, I try to limit the Y. Okay, and that almost worked. Okay, so look at the first number. Look at that. You see I'm getting big numbers in the first number, and the second number isn't changing as I'm going up and down. Okay, now if I come over here like this and I go, this is turning out to be kind of hard. Okay, look at that. The first number, X, isn't changing, and I'm getting numbers. I'm seeing numbers as high as 9. Okay, I'm seeing numbers as high as 9 in the second number. All right, that's 9 meters per second. That's the acceleration that I'm able to get just moving this thing back and forth. Okay, now I don't like operating in meters per second squared. I like to think in terms of G. I want to know, am I pulling 1 G? Am I pulling 0 Gs? Am I pulling 2 Gs? And so what I want is I want to convert these meters per second, I want to convert them into Gs. And how would I do that? Right here, what I know is I know that there are 9.81 meters per second. Does that ring a bell? That is the acceleration of gravity. So if I take that number and I divide it by 9.81, I go from reporting in meters per second into Gs, okay, into simple Gs. All right, so now I'm going to divide that one by 9.81, and now I've done that conversion, and now when I report it, when I download it, did you guys understand what I was doing? You see, this was allowing me to move only in the X direction because I was staying pressed against the phone. And that way I'm not moving like this. So as I'm trying to move, it keeps it restrained. Hopefully that made sense. Okay, now what am I reading here? Look, I'm reading 0.02 Gs. I'm almost at 0 Gs. I'm almost at 0 Gs. The 0.02 is what? It's offset error. While this thing is sitting still, it should be what? It should be perfectly still. Okay, now let's look at the first number. Look at that. I'm trying to see if I can get to 1G. I think, yeah, I saw some I got there to 1G. And now I'm going to come over here like this. And now I'm going to go the other way. And yeah, look at that. I'm getting up to 1G just by moving it like that. Okay, you guys, you have your code, you have the thing hooked up, and now play around with it and watch those numbers and see what you can do. What is your homework assignment? Okay, so look at this. While I'm sitting still, I'm reading 0 G's practically. I'm reading 0 G's in X. I'm reading 0 G's in Y. And then what is your homework assignment? Your homework assignment is to take this program and to add the Z axis, okay? And then I want you to print X, comma, Y, comma, Z, all right? Now, I want you to predict, what are you going to measure for the acceleration in Z? Now, I want you to measure Z, and then I want you to look at it, and then I want you to say, I got the expected result or I got an unexpected result. If you got an unexpected result, then I want you to think about it and explain why you got an unexpected result, okay? So that is your homework assignment. Man, I hope I didn't bore you to tears with this. And again, I know a lot of people, what do they want? They want me to show the schematic, they want me to give them the code, and then they want to go off and run measure acceleration. But, guys, I want you all to really understand how these things work. I want you to understand how they work. And so that's why I go into the more detail on it. And so get your homework done, post your homework, leave a link down below to your homework so I can see how you guys are doing on the homeworks and doing in the class. And also at this point is when I always give a shout out to you guys who are standing with me on Patreon. It is the Patreon support that allows me to continue to create every single week fresh, new, in-depth quality content. So really appreciate you guys. You can also help by giving this video a thumbs up and leaving a comment down below. That'll help me with the old YouTube juice. If you haven't already, make sure you subscribe to the channel. When you do, ring that bell so that you'll get notifications when future lessons drop. And most importantly, share this class with other people, because the world needs more people thinking like an engineer and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.